So like trapezoidal rule and rectangular approximation rule, Simpson's rule is used when either we're working with a table of values instead of a function, or we might be working with a function that doesn't have an antiderivative, or when an antiderivative does not exist. So that is when we would use Simpson's rule. And again, it's used to find the area under a curve. So we have lots of ways of finding area under a curve. And then I guess just to kind of summarize while we're here, we'll have a little side bubble for a summary. The most accurate method is using the antiderivative. The easiest method, so that's the most accurate. The easiest method is rectangular approximation method, which is why those are the more heavily emphasized. Then the next most accurate would be Simpson's rule. It's the most accurate of the approximation ones. But it is a little bit more difficult, so we don't use it as often, but it will be asked of you on the AP test. And then fourthly, we have trapezoid rule. These are all the different ways of finding the area under a curve. This is medium accuracy, better than rectangles, not as good as Simpson's. So yeah. All right. So Simpson's rule basically uses a formula of a parabolic curve. So believe it or not, there is a formula for a shape that looks like this. So let's say it has these two straight sides. They could be different length or the same, but a curved top. Let me make this a little bit more exaggerated. I keep doing this. It needs to be more exaggerated so you can really understand what's going on here. A curved top, not a straight top like a trapezoid. And there is, in fact, a known area for this type of shape. But you have to be able to split this area evenly in half, otherwise it won't work. So you can only use Simpson's rule, and you should probably write this down. You can only use Simpson's rule when, I want to word this nicely, when you can split the interval evenly into an even number of subintervals. So only when the interval can be split into an even number of subintervals. You have to have an even number of subintervals for this to work. Okay, so let's label some of the pieces here. So we're going to call this half H, and since it was evenly split into, the other half will also be H, similar to the trapezoid. The bottom part was considered the height, so to speak. We're going to call this L for left, M for middle, and R for right. And the area of this shape is H over 3 times L plus 4M plus R. H again is half the length of the base. L is the left height. M is the middle height. R is the right height. H divided by 3 times L plus 4M plus R would give me the area of this shape. Okay, so here's how Simpson's rule works. And I think I'm going to need to go onto the back side. So let's say we've got our curve that I like to use all the time. And I'm finding the area under this curve from A to B. Let's go ahead and just call this Y. Well, I need to be able to split it into an even number of subintervals. So I'm going to go ahead and split it. Let's first go like this. So I'm going to have 3 big shapes, and then I'm going to split those in half to make 6. Okay, so let's call the A again. We'll call that x sub 0. This will be x1, x2, x3, x4, x5, and then B will be x6. I'll go ahead and put in parentheses x sub n because the 6 is just sort of this generic example. But when you're doing these, it could be anything. So we let it be n to let it be whatever we need it to be. Okay, so y sub 0 would be this height. You know, the distance from this point x0 up to the top of the curve. This would be y1. That would be y2, and so on. Because it's what you get when you plug the x value into the function. So it gives us the y values on this curve, which are the heights. Okay, so if I were to try and add up, and so notice I have basically 3 of those Simpson's rule shapes. I've got 1 right here. Whoops. I've got 1 right here. I've got 2 right here. And then I've got the 3rd one right here. So I'm going to find 3 of those areas that we looked at before and add them up. So I would have h over 3 times y0 plus 4 times y1 plus y2. That goes with Simpson shape number 1. Add that to Simpson shape number 2, which is h over 3 times y2 plus 4 times y3 plus y4. Okay, that was Simpson shape number 2. And then I'm going to add that to Simpson shape number 3, which is this one here. And I'd get h over 3 times y4 plus 4 y5 plus y6. And if I added this all together and combined all my like terms, first thing I notice is I could go ahead again and factor out the h over 3. Each one of those had that in common. I have 1 y0, 4 y1s, and 2 y2s. And then 4 y3s, 2 y4s, 4 y5s, and then just 1 y6. So this is a formula where there's 6 x values. If I wanted to generalize that to allow for however many y values, it basically would generalize like this. The first one only has 1 of the y values because I'm only going to use that first height 1 time. Then because of the formula for Simpson's rule, which makes you multiply that middle height times 4, the second y value will always have 4 of them. And then because of the fact that this third x value is going to be used twice, it'll be used for the first Simpson shape as well as the second Simpson shape, there would actually be 2 of those. And then it alternates from there, back and forth, until you get to the second to last one. So actually the third to last one and the second to last one. The third to last one is always going to be, let's continue down here, is always going to be 2. And so that n minus 2 just means it's the third to last y value. The second to last is always going to be 4. And then the last one is always going to be used just once. because it's this height right here, which there's nothing on the right of it, so it's used only once. So this right here is the general rule for Simpson's rule. Very similar to trapezoid. It's just now you're taking those changes in x and dividing by 3 instead of 2. And then the middle y values are alternating between 4, then 2, then 4, then 2, and then blah, 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 and then 2, 4, 1. And so again, the only way this is going to work is if you have an even number of x's. You don't need an even number of Simpson's rule shapes. Like here I only had 3 Simpson's rule shapes, but I split each of those shapes in half, creating 1, 2, 3, 4, 5, 6 intervals. You have to have an even number of intervals for this to work, so just keep that in mind. Okay, and then for our next video, we're going to go ahead and apply this.